from large industrial applications to applications in the medicine field. So and for laser melt processing of the mixture of nickel oxide and iron oxide that we made into a pellet, we used a patented laser furnace that we have, and we use a small version of this. We have several of these laser furnaces in the laboratory, and we use a small version to explore the microstructure and magnetic properties and produce dense monoliths, which are convenient for the production of nanoparticles via laser ablation. Because when you produce these laser ablated nanoparticles, you want your target to be as uniform as possible. Otherwise, your nanoparticles will have a variation in size, in composition, etc. So the idea to use the laser furnace is twofold. And it's not written here. It's twofold. It's because we want to produce something which is uniform and it has controllable surface characteristics. And at the same time, we know that if we do that, maybe I will do that. I'll comment that in a moment. And so then these were carried out, these experiments. I will tell you what I was going to tell you now. I went a little bit ahead of myself. This is a 4-meter long laboratory furnace with a 350 watt CO2 laser. And the material that we want to process passes through a thermal curve. So it starts at room temperature. It increases to a maximum volume temperature, which is where the laser applies intensity. And then it cools down also with a cooling curve, which is determined by the speed at which the material goes through the furnace and the profile of the temperature in the furnace. So let me show you then why we use a laser furnace. Because nickel ferrite is a ceramic, and like most ceramics, it has this problem of suffering from thermal shock. With sufficient thermal gradient, the thermomechanical stress is not assumable by the material, by most ceramics, and they break. And so this forces us to invent this device, which we call a laser furnace. And you see here, working in large scale. This is a 15-meter long furnace in a project we did. And this is the resultant products. In this case is brick. And you can see you can get very different surface finishes, even with the same clay. So that depends on the emission conditions and on the on other parameters like the traverse rate of the materials going through the furnace. Even when they are misaligned, they come out uniform, and this line is very well aligned from the laser. In this case, in this prototype we had 2 lasers on top and bottom because we needed to treat 4 surfaces of the brick. So this is just to show you that you can solve very complex geometries and difficult geometries with laser optics and mirrors in a not so difficult way. So this is the one we have now, but this is also a 13-meter long furnace, which we use now in a glass company that we founded, that we are sponsors of, Professor Anguel and myself. And this is typically what you see when you put a sample in the furnace. This is an exaggerated sample because this is a refractory ceramic. Here it's around 900 or 1000 degrees Celsius. And now you will see how extreme the conditions for the surface are when the laser comes in and basically draws a line on the surface, on the top surface of this ceramic. And this goes up to 1900 degrees measured, and where the laser melt is taking place there. And you can see you have a stable line. It goes through the material, and the material does not break, does not shatter, which is typically what would happen, and you have seen in the videos before. So with this principle, we can make, this is a 60 by 60 centimeter surface, which with a very nice surface finish. It's a glazed ceramic, and you can see these metallized ceramics with gold and platinum, and you can see very nice colors in this. This is an A4 size ceramic. So these are just typical examples. So this is a scalable method. So we can use this with relatively ease of scalability. So This is a representation of the furnace we use for this process that I tell you today. And it's basically the same. It's just 4 meters long. It looks much smaller here. And what we do here is we generate a melt pool because we use a CO2 laser, which is eminently thermal. And it just excites phonons immediately in the material where it's focused, and it generates heating, very intense heating and melting. And the material is moving through at a constant speed, so it leaves a surface with a certain depth treated and with the microstructure changed from the beginning, from the original microstructure. And you can see that here, just at the naked eye. This is the original pellet of the mixture of nickel oxide and iron oxide. It's a mixture, it's not reacted. And this is the resultant in 2 different conditions. And so you can more or less see there are elongated grains along one direction, and this is because this is a highly anisotropic method of treating the material. So the grains grow perpendicular to the laser line, which is the melt line. So this has been studied in our laboratory in other configuration. And this is done at a surface temperature of 1000 degrees and at 1500 millimeters per hour. And with the laser scan rate, that means the laser is moving, let's say, it was moving this way very fast and making a line, much better than the one I made here, but this was at 15.9 meters per second. So the line essentially is stationary. And you have a stationary melt, which is a line on the whole width of the material. And what we did, we studied, I have shown here, I will show 3 different samples, where we increased the laser power from 1 to 2, and also from 2 to 3, because we decreased the line width. This line width is the line that is scanning the laser. So if we have a 70 millimeter line width, we have much more area illuminated by the laser, and so we have a decreased power density. So this means that our power density increases when we go down to 50 millimeters. So this is a more aggressive treatment. I don't know how I'm doing on time. Is it okay? So thank you. So these are the 3 samples. You can see here, this is the low aggressive conditions, lower power density, lower energy input also, and this is an intermediate one, and this is the highest, most aggressive condition. As you can see that apparently we have a much better surface finish, and more melting has been much more uniform throughout the surface. We can see that this is the augmented micrograph for each of these, but I think you can see it better here. If you look at the cross section, you can see the lowest, least aggressive conditions. They hardly melt a very thin layer of material. The surface roughness stays the same as it was originally, essentially. And when you go to the highest aggressive conditions, then you can see you increase the melt layer thickness significantly with respect to the other one, and improve the surface finish. And also you increase the effect of the volume that the depth of, or what we call in laser processing, the heat affected zone in the material. And so basically this okay, this is the experimental procedure. Once we fabricate this, but I don't know why this is here. I think it got tangled. I will go back to this. This is the same that I wanted to show you from before. This is what is published in the paper, and you can see, maybe you cannot see because of this light too well, but you can see how the melt thickness has left a much thicker layer in the material affected, and also a much better surface finish. Yeah, thank you. So now you can see maybe a little better. And you can see also here, you can see this is the original one with a low intensity condition, intermediate and high intensity conditions, you can see the surface improves, and this is a sign of melting. And when we take a look at the X-ray diffraction, we see the diffraction lines which correspond essentially to the nickel ferrite spinel, although there's small traces of iron oxide left there. And if we look at the nanoparticle preparation, then I have redone these conditions that I had before. And we use pellets. These pellets are about 20 millimeter in diameter by 3 millimeter thickness. They are immersed in distilled water, and we use an 800 picosecond pulse with near IR laser with a level of power of about 5.4 watts and 300 kilohertz pulse repetition rate. And we make a continuous beam raster of 7 by 12 millimeter area at 50 millimeters per second with a line-to-line distance of 15 microns. So we make many lines and we separate them 15 microns between each other. We can calculate the radiance of each pulse. It's about 1.4 gigawatts per square centimeter, and this is done during 5 minutes. And this is how we just generate nanoparticles in the liquid, so they get suspended in the liquid. The laser is transparent to the liquid, so it just interacts through the liquid with the target. The target is heavy enough to be stable in the liquid, and what we are doing is just removing particles not to the air, as in a dry system, but that will be suspended in the liquid. And then, since they are magnetic, they can be easily separated from the liquid. So this is what they look like. You can see there's at least a bimodal distribution of some large particles, which you can see here above or around or above 100 nanometers in size. And then you have the largest fraction is below 10 nanometers in size. And of course, we cannot measure the ones that are very small. This is done statistically by measuring the nanoparticles here. And you can see also a sort of a bimodal distribution here with the very small particle size. And this is about 3 nanometers is about the more or less the medium size here, or the maximum in the distribution, although it's not really symmetrical. So it's like shifted to the right on a hump. But then you have also a distribution here, and you have the large ones that you see. And I could explain, I have ideas to explain why, and I think in the paper we wrote some of them, but I don't think I will have time here. I can do it, if you ask me, I can do it. And this is the X-ray diffraction of these nanoparticles that show that we have the nickel ferrite. So then we have kept the nickel ferrite composition, even though we have made the nanoparticle go through this very aggressive ablation process. But we are doing it in sub-nanosecond regimes, which are relatively respectful with the material. If we were doing it in, let's say, 100 nanosecond regime, we would have large melting, and we probably would have lots of spheres which would not be able to crystallize because they would cool down very fast from this very intense melting. But in this case, of course, as we go to very short pulse lasers, what we do is we favor removal of grains and nanoparticles by a different mechanism and avoid melting, which sometimes may be detrimental to crystallinity. So in this case, we have the ferrites, and this is the objective of this work. And so I think I can conclude that the laser furnace processing is convenient to prepare nickel ferrite dense targets for laser ablation. And the reason is, with lasers, unless you do heating at the same time, it's very difficult to work with these ceramics and not break them, so that they will be destroyed on the way. So they become useful because we use this laser furnace technology. And when we combine this with underwater laser ablation, then we can get small size, medium size nanoparticles, which maintain the original structure of the spinel. And both methods can be really scalable in both cases, although we have ideas on how to scale the underwater laser ablation method, because we have done it in the past with industry for other materials. But we know both of them are reasonably scaled, and you can find All this work published with much more detail on these publications with our friend Bekir Özçelik and his group and our other colleagues. I would say, what is next? Probably the use of near IR laser sources would be an advantage in the laser furnace. We use the CO2 laser. This is much more aggressive on the surface. It does not penetrate so much. And so we will have a much better control of the melt in the process if we use a near IR laser. We can use also femtosecond lasers, which we now have in different wavelengths, to reduce the particle size and the particle size distribution, most likely. And we need other improvements, such as we know several improvements as we have made with industry in the past, so we can do a continuous process of nanoparticle formation. And I would like to thank you all for your attention, and again, the organization for the invitation. Thank you very much.
Straight by laser. What do you mean that homogeneity? I mean, it's not chemical homogeneity, is it?
Also, everything.
Can you explain?
Chemical, microstructural, and surface roughness, because they're all important when you do laser ablation. You're talking about the target.
Yes.
Yes.
Target preparation.
This is a process which we have been working now for many years, but usually we work at speeds with the superconductors also, and we have collaborated also with Professor Bekir Özçelik. In this superconductor processing, what we try is to control the microstructure and elongate the grains, and with a very high level of anisotropy. And we do this at speeds of about 30 millimeters per hour. And here we are in 1500. So this difference goes towards a lack of crystallinity. But surprisingly, in this system, we still have a crystalline result, so that the surface is still nickel ferrite spinel. But it's surprising to us. If you do that in the superconductor, you have something which is like a glass because of the nature of its composition. And so one of the things is you can get, if you go very fast, and our colleagues have done this in other materials, you can get a nice glass which has a uniform composition. But you can also get a nice crystal. And this is just from the composition point of view. But then if you go at the correct speeds, you can also elongate grains, and you can get a microstructure control. And this microstructure may be uniform or not, depending also on the phase diagram of the system. So, and depending on, this is a zone melting system, so it carries away impurities. Sometimes you incorporate impurities and you increase the concentration of impurities so much that you have a sudden crystallization of these impurities, and then you start again from zero with zero impurities, and they build up again. So you can have a system which crystallizes or solidifies in let's say in a periodic fashion. So you don't have a uniform system, but you have a periodic system with changes in composition at certain periods. And the other one is the roughness. Surface roughness, if you notice, is most satisfactory. That means more flat, much lower surface roughness when you melt more material. So when you melt really well, then you can spread the melt very nicely, and you get sort of like an almost polished surface. If you don't melt well, you have the original roughness. So as you melt more, you take away the original roughness into a much less rough surface, as you saw in the example that I gave from ceramics.
All these things help to prepare better nanoparticles.
Yes, because what you want to do by laser ablation, what laser ablation does is evaporate material from a target with a specific composition and specific surface roughness and specific microstructure. They all affect how you evaporate material. And so if you have a change in surface roughness, there is a change in absorption. And so the efficiency of this evaporation changes. And this could mean that you have a wider distribution of sizes in your nanoparticles. So if you want to have a controlled size and size distribution of nanoparticles, then you should have a uniform target.
Understand. Any more questions from Salon? Any questions from the... okay, I have one more question actually.
No problem. But don't make it too difficult.
No. It's very simple. When you use distilled water to collect the nanoparticles you produce, do you have any color change during the process?
have to ask Bekir because he did it himself also. and Sesen. Many people have done this. Yeah, we had in the past already. We did this with gold. With gold, you see very nice changes because you have the plasmon effect.
Can you try other liquid mediums instead of water?
There are several, I think.
Yes, you can try. We have tried in the past others. You can try with different liquid media because then that will affect. There's studies in the literature. This is a very hot topic in the literature. There are several reviews that we cite in our papers. Several really good reviews and very exhaustive reviews with all the mechanisms proposed and so on. And there's a lot of studies with different liquids, and there's still room for a lot of improvement. And so now our next idea is to go into femtosecond lasers and also into a continuous reactor, as Becky is saying, because you need to remove. This is very easy to remove. Gold is not so easy, but this spinel is very easy because you put a magnet and you remove them very efficiently. So you clean the water and you start again. And if you do it continuously, you can have a continuous production, which is much more effective. Because when you have the problem that Becky was saying, the nanoparticles produced are blocking the laser. And so they're reducing the efficiency of the process. So that is, yeah. Thank you.